variable bindings in Rust. There are a lot of different ways that variables can be bound in various languages. Sometimes you have really strict languages that require defining the type of data that the variable is going to be associated with. Rust is this language, and it does this specifically for safety purposes. It allows us to do extra checking at compile time that helps the compiler help you write better software. Because it's really easy to do a whoopsie and then accidentally assign variables and overwrite variables or put data where it didn't mean to go. So if we take a look here at Rust's variable bindings, they have some nice quality of life improvements as well. Usually in strict static type languages, you need to always define what kind of data the variable is going to be holding. And very often, the variable can be determined through context, which reduces the annotation burden. And the annotation comes from you. You are the annotator. You have to annotate your variables. And if we take a look here, this is an integer, but it's not really saying, other than the name of the variable, that it's actually an integer. The compiler doesn't know that you intend this to be an integer until you give it an integer data assignment. Yes, there's a U32 on here, which does it does give a little more than a complete idea of what this is. We probably can do something like that. The compiler will automatically know that this is an integer and assign the default integer type, which I believe is U32, could be U64. Okay. So we're close here, I32. So it's an assigned integer as the default type. So if we remove this, this will be assigned integer. And look, there's not really any annotations that are around here. The compiler will say, okay, you're very pretty sure this is going to be an integer. Same thing with the Boolean. And in this case, this is sort of a null value, an empty tuple. It's a null value. You can also reference other variables, and the compiler will understand without you having to annotate the kind of data that this is. And this is an annotation example here, I32. You can do :I32, and this will tell the compiler what you are intending. But you don't have to do that. The compiler can figure it out. So I click the compile button, fully expecting, because Rust likes to do this in a Rust by example, fix me here, and the compiler will complain. It didn't complain this time. Usually it'll say, hey, sorry, it's unused variable warning. In this case, it's just a warning, right? So this is not disallowed. It's just unused code, right? Well, clearly it worked this time. So you're supposed to do that. You're supposed to add an underscore on it where it means that you intend to not actually be using the variable even though you're assigning data to it. And we're getting the exact same output. Mutability in any programming language is the ability to change data as it's defined. You can define a variable like an integer, like the number 1, and you might want to increment that number by adding 1 to it. A common operator is like the plus operator, the plus equal operator, or reassigning the variable to be equal to the variable itself plus 1. For example, these patterns are not common patterns or even possible in Rust in some cases. You can do these using certain syntaxes. You've got the A++ you've heard of, you've got A plus equals, and A equals A plus 1. These are mutations. By default, all variables are immutable, which means you just can't change them. No changing variables. You need to specifically annotate with the MUT for mutable. If you want to mutate, you have to say MUT. Then you can use a plus equals operator, which increments by 1. And if we run our compiler here, we see that we are attempting to mutate an immutable variable. All variables are immutable, unchangeable. You can't change them. You can't add to them. You can't remove. There's just no mutation unless you say it is mutable. And so we have an example here where we're attempting to mutate this variable that is not defined as mutable. The compiler is just going to say, nope, sorry, you can't do that. Oh, did you mean mutable? Okay. Well, just put this in front of it. There we go. And then if I click the play button, is it going to work? There we go. Okay. Now it's happy. So this is an interesting thing in Rust. Rust will always default to immutable, unchangeable variables. This is just kind of, I would say, unique to Rust. Every other language kind of expects you to have variables that you're gonna change over time. Rust just doesn't do that by default. And there's many scenarios where you can be perfectly fine with never having to mutate any data. You can just reassign and include data in new definitions, which is also a really good pattern. However, sometimes you do need to mutate, like in a simple incrementer. Scope and shadowing in Rust. These are very specific programming terms that represent where variable bindings are going to be placed in the world of the constraints of the compiler. Most languages allow you to take advantage of these capabilities of scope and shadowing. The most common languages in the world, like JavaScript, Python, they let you do these things. In Rust, a scope is anything kind of, you've got the file itself, and then you've got these curly braces. And anywhere you've entered into a curly brace set, this is going to count as a new scope, a nested scope, or completely different scope. Variables defined in those scopes will only live as long as they are inside those curly braces. That's actually pretty straightforward. Just you've got your curly braces here, and then you've got your variable, and then your variable can live inside the curly brace. Once it exits the curly brace, it's gone. It's gone. You can't do anything. You've defined it in the scope. It's gone afterwards. There's no way around that. You might want to be using. You're like, wait a second, but I might need. Yes, you're right. You might need to be able to pass data around in various situations. Well, good news. We will definitely talk about that through passing data by reference and borrowing, which is like the Rust's way of calling passing data around is through borrows. This lets you keep that data that's defined within its own scope to be passed forward into a completely different scope that's somewhere else in a different file somewhere. Or you might be passing it off to another core on the system through multiprocessing or another thread. Rust is really great. It makes a fantastic experience for implementing those situations. Meanwhile, we're just keeping things simple. Scoping is straightforward. Okay, now here's the one that is confusing is shadowing. Let's talk about shadowing really quick. Shadowing sounds like something, ooh, what is this? It sounds powerful and mysterious. Why would they call it shadowing? Well, actually, it's kind of really simple. Variable shadowing is allowed. Although I don't know if I technically would want variable shadowing to be allowed. It allows you to redefine the same variable name again in a different scope. The problem with that is you're overriding the data because you could access this shadowed binding here of data here to be printed. And if I print this out really quick, you can see my shadowed binding here is going to print inside an inner scope, and it's going to be 1. But you can override it here and even change the type to a string, and then it prints out as a string, even though the variable name is identical. Now, I kind of think this is a bad practice in general because it's going to provide confusion. There's situations where it might be useful. I don't know if it can be. I can see where it might be unavoidable, or a scenario where it is almost the same data, but you want to change things around, or you want to mutate it. You might be able to do something like this. So unmutable data +1. Oh, look at that. Okay. So this is kind of a neat little trick to an unmutable variable. Using the same exact name, you can essentially make it look mutated. So it starts out as 1 and ends up as 2. So this is kind of like an okay situation. If you're completely changing it and making it something different, that's just causing confusion for future and later. You just don't, it seems like it's not a necessary scenario. But good news is, if you need it, it's there for you. Oh, and once you leave this area, you notice that the variable itself, the shadow binding variable, it goes back to what it was before it was modified and redefined. So only while it's in the inner scope temporarily is it mutate. Well, it's changed essentially, right? I count that kind of it. It's not technically mutation, it's shadowing. Rust allows you to declare variables first before assigning them any data. This is actually pretty useful in a lot of situations where you know that you're going to be using a variable at some point here in the future and you want to assign data to it, but you don't have the information yet to assign it. So you can initialize the variable by just using the let keyword and then the name of the variable and a semicolon. That's it. A really straightforward, here we go. Here's an example declaring a variable binding, but there's no assignment. Oh, wow, look at that. Okay, so even though we're in an inner scope here and we've created the assignment of the variable, it ends up being 4, even though it was nothing to start with. So it's basically 2 times 2 is 4. And then you leave the scope because the variable is defined above that inner scope. It's still available to be accessed and read from. And so you can print it here. Pretty neat. Also, you gotta be careful if you define a variable without assignment and you attempt to access it through a read, there's no data for it to be read from. You're trying to print out a data that doesn't exist. The compiler will catch this for you and complain, and it will look like this. Binding declared here, but left uninitialized. You didn't assign it to any data. It's giving you some hints here. It says it's used in the print statement, but it is possibly uninitialized. It's declared, but not initialized through an assignment of data. So all you gotta do is say 1. But if you do that, then this will fail. So you say mute. Let's do 0. Now I don't even have to comment out the line. I'm pretty sure it'll just work. And there we go! The Rust compiler brings to us a neat little trick with freezing data. We can freeze our data based, even if the variable is mutable, you have a way to actually freeze the current state of that mutable data using the freezing technique. Data that's bound by the same name immutably. Oh, it's got to be the same name, does it? I don't think it does. It could be a different name. Does it have to be the same name? The idea is that frozen data can't be modified, which makes sense, right? That's the whole point of something frozen. It's kind of like it's stuck, it's there. Unless you unfreeze it, you can't change it. Oh, okay. I see what the trick. Oh, okay. This is going to bring even more confusion. We got to be careful with this one as well. So you've defined a mutable variable, which you can change to any integer value that you want within an i32-bit range. Then you use a shadowing approach where you redefine in a new scope the same variable name to this variable name with the higher scope, but you don't define mutability. So this variable is shadowing the original variable in a higher scope, but itself is not mutable. So whenever you try to mutate the variable itself that you've defined in the inner scope, it's not going to let you. The compiler will be like, nope, it's not a mutable variable. And it will prevent you from compiling your application until you leave the scope and then you mutate again. Even though the variable name's the same, you can then mute it. You can mutate the data. It's like, okay, mutable now. So, okay, so that is kind of neat. I kind of get it. So you want to sort of freeze the state of that variable. So that way, essentially, there's no way you possibly could mutate the upper scope variable inside the inner scope. I kind of see a potential meaningful value to that. You're bringing in data, but you want to make sure that you don't modify it. And you're enforcing this by redefining the same variable, the same name, without a mute annotation. It brings a level of safety, and probably in general is a good practice. I think that's actually pretty powerful. So even if you wanted to, like, say, mutate the upper variable, you couldn't because the shadowing is overwriting it. So there's no way for you to do a whoopsie or any kind of accident in this case. One thing I want to try to see is what happens if we don't use shadowing and if we mutate the variable at a higher scope with the variable that we have defined in our inner scope. So I'm going to reference this like this. So A is going to be, is it a reference to or a copy? It might be a copy being that it's an integer. Let's see what happens. Okay, I've got a simple example here where, well, we're not shadowing anymore. So let's get rid of that comment. All right, so I've got my mutable integer that's defined as 7. I'm going to assign A to the mutable integer and print A. So that should be 7. When I click the play button to compile this, it should be 7. A will be 7. But then I mutate the mutable integer. Is A still 7? I think it probably will be. Let's find out. It is, okay. Even though I mutated this value, A is still going to be 7 because this is a freezing approach. I just grabbed the data here and essentially locked it into the A variable. Even if I change the original variable, A is going to maintain itself. So this would be another approach of using freezing without shadowing, which lets you mutate the variable, but also keep the current state upon entry into the scope, the inner scope.